Alright, so this is going to be one of our first videos where we actually do a problem on projectile motion. So we'll start with assuming that we have somebody standing here and they're just going to throw a projectile. Let's say they have a ball, and they're going to throw that projectile at an angle of 30 degrees with an initial velocity of 20 meters per second. So the questions that we usually get asked out of this is, how long is the ball in the air? How far away does it land? How high up does it go? And you'll be given maybe this much information. And it doesn't seem like a lot, but we do have quite a bit of information. So what do we know? We know our initial velocity is 20 meters per second, and it's at an angle of 30 degrees. So one of the first things we should do is realize that we can break this into vectors VIY or VYI, the velocity in the y, initial, and the velocity in the x initial. And the velocity in the y initial is just our VI times the sine of 30 because it's opposite the angle. And VXI is just VI times the cosine of 30. So when we plug this in, we get 20 times sine of 30 is a half. So that should be 10 meters per second. The cosine of 30 is 0.87. So 20 times 0.87 is like 16 plus 1.4 is 17.4 meters per second. We see that we have an initial in the y and an initial in the x. And then we're going to use our equations because it's two independent motions mapped together. And the one thing that will always link our two independent motions is time. Remember, in the y, this is like something's going up and then coming down. And then in the x, it's just moving along. And when you put those two dots together, you get something like that. How long is the ball in the air? How far away does it land? And how high does it go? We can solve for how high does it go, because we remember at the top of the parabola, Vy equals 0. As we have all of our standard motion equations, we just have to plug x's and y's in. So we always have that V final is equal to V initial plus A delta t. We have V final squared is V initial squared plus 2A delta x, or that could be x or y. And then we have x final is equal to x initial plus V initial delta t plus 1/2 A delta t squared, where these x's could be y as well. In the y, if we want to know how much time it takes to get to the top, t to the top, here's what we're going to do. We can take advantage of the fact that Vy final is equal to Vy initial minus 9.8 times time. And we know that Vy initial is our 10 meters per second, and Vy at the top, Vy final at the top is 0. So what this tells us is that 0 is equal to 10 minus 9.8 t, or t to the top, which is this, t to the top is 10 divided by 9.8. So our t to the top is 1.02 seconds. All right, once we know our time to the top, we can do one of two things. We said that this was a parabola, so parabolas are mirror images on both sides. So that would tell us our t total then is equal to 2 times t to the top. So our total time should be 2.04 seconds. And we're going to check that with some other methods, but we'll use that for right now. So once we know our t to the top, what can we do? We can use our position equation to figure out how high up it goes. So we'll assume that x initial equals 0 and y initial equals 0, y final, which is y at the top, is equal to y initial plus vy initial times our delta t minus 1/2 of 9.8 delta t squared. So y to the top is 0 plus our 10 times our delta t to the top, 102, minus the 4.9 times 1.02 squared, because we're looking for our position at the top. So y to the top, how high up are we? Looks like we're 10 times that is 10.2 minus this 5.1. So our distance to the top is 5.1 meters. It's going to go up 5.1 meters. 5.1 meters up. And then it's going to come back down. How else can we check our total time in the air? Well, let's do this. This is a position equation. Y final is equal to y initial plus vy initial delta t plus 1/2 ay delta t squared. So if we throw this ball up at this angle, it's going to take a parabola and it's going to land back at the ground where it started. So y final over here is 0. Y initial is 0. We have plus our 10. We don't know delta t. Minus 1/2 of 9.8 delta t squared. So what we see, 0 equals 10 delta t minus 4.9 delta t squared. We can factor out 1 delta t, and we have now 10 minus 4.9 delta t. What we can see is that one of the times t equals 0. The ball is at the ground at t equals 0, which makes sense. That's this solution. The other solution we have is that delta t is equal to 10 divided by 4.9. So if we plug in this to here, this term becomes 0. And that's when the ball lands back at the ground again. And if you take 10 and divide it by 4.9, you get 2.04 seconds. Our two answers are good. We know that the total time in the air is 2.04 seconds. Now, how far away does the ball land? We take our x velocity times time. Because if we start with this equation over here, x final is equal to x initial plus vi delta t plus vix delta t plus 1/2 ax delta t squared. What we see is that x final is equal to 0 plus 17.4 times our 2.04 seconds plus 0, because there's no acceleration in the x. So x final is how far away the ball lands, and it looks like that's about 35 meters. So the ball lands 35.5 meters away. And so we've basically used some of our kinematic equations. We used x equations and y equations. We linked them through time. We took advantage of knowing that Vy equals 0 at the top because the projectile slows down, comes to a stop, and then gravity speeds it back up, heading towards the ground. We solved for the 3 questions that were asked of us.